Okay, so before the midterm, we talked about the Fourier series representation for periodic signals. Right, so we looked at the Fourier series representation for periodic signals. Okay, so these signals could either be continuous time, let's say x of t, or it could be discrete time, let's say x of n. Okay, so if a Fourier series representation exists for this periodic signal, then this means that this periodic signal, x of t, can be written as a linear combination of complex exponentials. Okay, so in particular, as given here, you can write it as, summation of ak e to the j k omega naught t, right? K going from minus infinity to infinity. Okay. And here, omega naught is 2 pi over capital T, where T is the period of this periodic signal. Okay? So this is saying that the periodic signal can be written as a linear combination of these complex exponentials, which are actually, harmonically related complex exponentials, meaning that all of these complex exponentials have the same period, capital T. Okay? So this shows us that a periodic signal with period capital T can be composed by, all these different, complex exponential components that all have the same period, right? You don't expect that it be constructed by any component that is of any other period, right? It's difficult to construct a signal with period capital T when you take components that are not of period T, okay? So similarly, if you're looking at discrete time, then you have similarly the summation of ak e to the j k omega naught n, right, where omega naught is 2 pi over capital N in this case, where capital N is the period again, and k here is summed only over n consecutive, capital N consecutive integers. Okay? So what's interesting here is that different from the continuous time case where you can potentially have infinite number of frequency components, in the discrete time case, you can only have a finite number of frequency components. Right? For example, if you're taking k from 0 to capital N minus 1, then you're looking only at frequency components omega that are 0, 2 pi over capital N, 2 pi over capital N times 2, so on and so forth, up to 2 pi over N times N minus 1, right? So these are the, N frequency components of Xn, okay? And each frequency component, it corresponds to a Fourier series coefficient, right? So this corresponds to A0, this is A1, this is A2, and so on and so forth. Okay? So for discrete time signals, we're looking only at frequency component that lies only within a 2 pi range, okay? That lies only within a 2 pi range. You don't necessarily have to take the index from 0 to capital N minus 1, right? You could take it from, let's say, minus n over 2 to, n over 2 minus 1, right? Still having capital N terms, right? And you will see that the corresponding frequency is always still within a 2 pi range, right? So, okay, the n frequency components here are, within a 2 pi range, okay? All right. Okay. So this analysis allows us to analyze what are the frequency components, okay, that are contained in a particular periodic signal x of t. Okay. Now, if you look at each one of these, right, each one of these, let's say, e to the j omega t, right, if you plot this on a complex plane, right, suppose you plot this on a complex plane, real and imaginary, then this, as time t evolves, right, this is actually a function that moves around the unit circle on this complex plane. Okay? So when t is 0, right, when t is 0, the real part is 1, the imaginary part is 0. So you start with this point, and then as t increases, you start to rotate in this counterclockwise direction when omega is greater than 0. Okay? Now, when omega is less than 0, right, you could be, rotating at the same speed, except you're doing it in a, clockwise direction instead, right? So this is when omega is less than 0, okay? So different frequencies specifies, different speeds of rotation around the unit circle, right? And the positive or negative sign determines which direction it is rotating in, okay? Right. So these are pure frequency components at frequency omega. And we show that by combining these pure frequency components, right, these pure frequency components at integer multiples of 2 pi over capital T, we can construct any periodic signal with period capital T. Okay. Okay, so this is more or less the insight about Fourier series representations. Okay. Now, what's good about, expressing signals as linear combinations of complex exponentials is because if we pass a signal, if we pass a complex exponential through a linear time-invariant system, then we know that the output will give you the same complex exponential scaled by some value that depends on the exponent, okay? And this is also the case in discrete time. Now, in a general case, right, this value, h of s or h of z, we call system functions. But in particular, when we're looking at the case where s is pure imaginary, right, when we're looking at complex exponentials that represent a pure frequency component, then this value h we call the frequency response, okay? And the reason for that is because this value of h gives us the response to the pure frequency component, let's say e to the j omega t when s is equal to j omega, okay? So this h is called the frequency response when we're looking at complex exponentials with pure imaginary exponent, namely a complex exponential that represents a pure frequency component. Okay. So then when you write your periodic signal x of t as a linear combination of these pure frequency components, then the output y of t will be the linear combination of the same frequency components, each one scaled by its frequency response, h. Okay? Now, to gain further insight on what this coefficient does to this frequency component, we also often like to write this in terms of its magnitude and phase. Okay, so for example, for AK, we can write it as, the magnitude, AK, times e to the j, the phase of AK. Okay? So I'm writing AK as the magnitude times e to the j of the phase. Okay? Right. So the reason this is interesting is because now the magnitude tells us how we scale this frequency component, right? If this value is large, it means that we have a large frequency component at this frequency. If this value is small, then this means that we have a small frequency component at this frequency, okay? And this phase, right, this phase sort of offsets the rotation of this sinusoid, of this complex exponential. So originally, if you look at this pure complex exponential, at time 0, you start from this point and you start to rotate. But now when you're multiplied with this e to the j of the phase of AK, this offsets when you start to rotate, right? You may start to rotate at the angle of AK, let's say at this point, right? And you start to go around this unit circle, okay? So if you look at a single frequency component, this phase offset probably, does not have much consequence. But when you are taking a linear combination of many sinusoids, right, of many of these frequency components, then different phase offsets may cause different constructive or destructive combination of these different sinusoids, okay? So through different amplification and through different phase offset, we are able to combine into any periodic signal x of t. Okay. So if you think about it, then what happens? What is the implication of this frequency response? Right. So when you say that the output of this signal here is the same linear combination of the same frequency components, but now each component is further scaled by this frequency response, then this means that the magnitude is further scaled by the magnitude of h, and the phase is also further affected by the phase of h, right? So in this case, the effective coefficient here would have a magnitude that is AK times the magnitude of JK omega naught, okay? And they would have a combined phase of the phase of AK plus the phase of HJK omega naught. Okay? So the linear time invariant system modifies the scale imposed on the frequency component, k omega naught, and also adds an additional phase offset to this rotation. Okay? And you have a different magnitude and phase effect on different frequency components. Okay? So this is essentially what this linear time invariant system does. And it gives us a lot of insight on how a linear time invariant system affects the signal through its different frequency components. Okay. All right. So this is the same for discrete time as well. All right. So in discrete time, xn is written as a linear combination of e to the j 2 pi k over capital N, n. Okay? And this is summed only over capital N consecutive terms, right? Like I mentioned, there are only capital N distinct frequency components in the discrete time case. Okay? And each component, right, so we're only interested in frequency components within the 2 pi range. Okay? So each frequency component is scaled by this frequency response. Okay? And again, right, since we're only interested in frequency components within the 2 pi range, we're also only interested in the frequency response over the same 2 pi range. Okay? And it doesn't matter which range we're looking at, because you can show that this frequency response is also periodic with respect to 2 pi. So it doesn't matter how you shift this 2 pi range, you will still get the same summation. Okay? All right, so maybe a note here. So this h of e to the j omega, okay? Let's say 2 pi k, sorry. Let's just write omega in general, okay? This e to the h of e to the j omega is periodic since, okay, if you take h of e to the j of omega is periodic with period 2 pi, since okay, if you look at e to the j omega plus any integer multiple of 2 pi, right, by the definition, this is summation hn e to the minus j minus j omega plus 2 pi k times n okay? And we know that since k and n are integers, therefore, this is adding the frequency with any integer multiple of 2 pi, which gives you the same thing, right? So this becomes summation hn e to the minus j omega n, and this is exactly h of e to the j omega. Okay? So this is just to show you that, it doesn't really matter which 2 pi range of frequencies you're looking at, right? The summation will give you the same thing. Okay. Okay. So like we just mentioned, for a linear time invariant filter, the frequency response specifies how you scale the magnitude or append a extra phase shift to each frequency component of the signal, okay? So if you are able to design your linear time invariant system to yield magnitude or phase variations that you want, then you can manipulate your input signal into any output signal that you would like, right? Okay. So this operation, right, is what we call filtering, okay? So like we mentioned last week, right, filtering is the process of eliminating or changing the amplitudes of the frequency components in a signal, okay? So there are different types of filters. One is what we call frequency shaping filters, which changes the shape of the spectrum, right, depending on the application that we're looking at. Okay. So one common application is the use in audio systems, where we can use a frequency shaping filter to adjust, let's say, the bass or the treble level of our sound system. Okay? Or we can also use it to perform equalization, okay, to compensate for the distortion caused by our audio speakers. Okay? And this is an example of this audio system that we showed last time. Okay? Now, another example, okay, is this so-called differentiating filter. Okay, so in this example, we're considering a system where the output is equal to the derivative of the input, right? That's why it's called a differentiating filter. Okay. So suppose that you let x of t, the input, be a pure complex exponential, okay? So because this system, assuming this system is linear time invariant, this means that the output, so we don't have to assume that, but suppose that you input a pure complex exponential, e to the j omega t, then the output would be the derivative of this, which is j omega times e to the j omega t, okay? So this is a linear time invariant system because inserting this frequency component gives you the same frequency component at the output scaled by the value j omega, okay? So j omega here is the frequency response of the system, okay? So the frequency response h of j omega is equal to j omega, okay? Now we can write this in terms of the magnitude and phase, okay? So we can write this as the magnitude omega times e to the j 2 pi over 2 when omega is greater than 0, okay? I'm sorry, e to the j pi over 2. Okay. Right. Because by Euler's relation, right, you can write this as cosine pi over 2, which is 0, plus j sine pi over 2, which is 1, right? So this term here actually gives you j, okay? Now, when omega is less than 0, right, then we would need the magnitude of omega times minus j, which is e to the minus j pi over 2. Okay? So in conclusion, this tells us that the magnitude of the frequency response is omega, and the phase is pi over 2 for omega greater than 0, and minus pi over 2 for omega less than 0. Okay. So when you plot this out, right, when you plot this out, you can see that the magnitude, right, of the frequency response looks something like this. Right? You have a larger and larger magnitude as omega increases, both in the positive and negative domain. And this magnitude, right, the scale imposed by the frequency response is smaller and smaller, right, as omega approaches 0. Okay? So this differentiating filter amplifies higher frequency components more compared to low frequency components, right? So it shapes the spectrum of your input signal by amplifying the high frequency components and somewhat suppressing the low frequency components, okay? So by this, you can see that the frequency component, e to the j omega t, receives larger amplification for omega for larger omega, and vice versa for smaller omega. Okay. Now, suppose you impose such a filter onto a two-dimensional image. Okay. So suppose you consider some image like this. Right. This is a black and white image. So the value at each point you can sort of view as the intensity. Okay. The intensity at each point. Right? So the intensity varies, okay, at each point. Okay. So if you impose so in this figure, right, you can sort of intuitively you can sort of see that for part of the figures that are more or less the same, right, for smoother parts of the image, this typically corresponds to frequency components that have a lower frequency. And for parts of the image, such as the edges, right, when you go from white to black abruptly, this typically corresponds to a higher frequency component, okay? So when you impose such a differentiating filter on this image, you will be amplifying the high frequency components, meaning that you're amplifying these components that specify, abrupt changes from black to white, basically the edges inside this image, and you will be suppressing the smoother parts of the image, okay? So if you impose a differentiating filter on this image, you will get something like this, where you can see that all these edges are amplified and the smoother parts, right, are suppressed. Okay? So this is one application of a frequency shaping filter. Okay. So you can also look at an example in discrete time.